So it constructs subgraphs and predict the propagate information. So we'll give you more example about the pin stage. The here slide give you the information about the IZMC, which is published 2020 IZMC. So from the user item matrix, we try to predict this one. To do that, at first it considers a subgraph like this. So in this subgraph, we have three neighbors, composed of three nodes. In this case, at first here, the first user connected to the 3, 5. So where is the user? So here, 3, 5 we have. What about the third one? It's connected to the 1 and 5. This one. What about this one? So this is what we are interested in, right? We try to predict this. This one is, this user is connected to 4, 2, and we don't know about the read this back to this item. That's why we put a question mark. Similarly, we can construct a subgraph from this instead of the whole graph. So when you see at the here subgraph, you can observe that user average rating is 3 and item average rating is 5. How did you get it? So item average rating here 5. User average rating using 4 and 2. This because this is, we don't know yet. So 3. We get this. And item total rating is 2. The similar user's average rating is 5. The similar user is so similar users average rating is 5. So this is from the subgraph. So, and number of path toward this blue and purple is 1 and 1 from the path. And we learned these information and train the graph neural network, and it is able to predict the 5. So now we have new subgraph to propagate information, and these information could be propagated and decide final recommendation as 5 like this. So I won't give you the details about this. So just here is prepared to give you the examples to construct the recommended system. So with this way, we can give you the partial observation to the predictive label. So the paper showed that this approach uses the partial observation, but the result was quite promising. So what about the aggregation? So we have looked at several example cases about the gap construction. So now we have another design choice for the aggregator. So aggregator is to decide the neighborhood representation. So to decide neighborhood, we may just aggregate the neighbor and multiply by the weight matrix and normalize from the number of neighbors. So here I'm saying that without normalization means so we don't consider degree normalization. It is just normalized by number of users. Here we consider degree normalization. So we additionally consider the neighbors, the elements in the neighboring nodes, and we compute this normalization constant and some is considering this the degree normalization constraint and decide the final the current layers the user representation. So this looks simple, and the aggregation strategy is classified into these two approaches. And there is no true answer, and depending on data set in your recommendation task, so you need to choose carefully. And the most of the recent benchmark, so with the degree normalization, that shows the better result. So, but you need to test it, and depending on your own data set. All right, and what about the importance pooling? So to decide the neighboring representation, let me come back to the framework. So here we decide the neighboring representation, and considering to decide this, the neighboring nodes could be used, right? But depending on the definition of the node definition, so the input graph G, when G is from the full graph, this will return the whole neighborhood. When this G is from the sampled subgraph, neighboring U is really, it depends on the subgraph sampling. In this case, we need to choose the neighbors carefully depending on their importances. So here, to decide neighboring node representation, we give different weight for the sampled neighbor and decide the neighboring representation. How would you give the weight? So to decide which neighborhood will be considered is we use random walk. We just randomly travels the neighborhood. We can count how many times the node is visited, right? For example, 1, 4, 1, 1, I don't know. We visited 2, right? So with this way, we can normalize their importance. In this random, we use just one random, and we can put, so we have 1, 2, 1, 1, right? 1, 2, 1, 1, and we divide 3, 4, 5, 5, 1 over 5, and 1 over 2, 5. So these will be used for the weight. The weight is used from the sampled node representation, which is given from the previous layer, and aggregate with this linear transformation with the different importance, and go through the neural network. So this is neural network, and now we have neighboring representation. And this one is combined with its own representation in concat, and decide the new representation of the node. So this is the importance-based pooling. So these aggregation functions determine importance of the neighbors according to the graph structure, but we ignore relationships between connected nodes because the importance is from the random walk, so it loses relationship between the connected nodes. It is just from the travels from the input graph. However, the interacted items are not equally representative to reflect user preferences. Researchers employ attention mechanism to differentiate the importance of neighbors. So from that idea, another recent work considered more complicated the aggregation. So I is the neighbor node. This is the concatenation as far as I remember. And we learned the representation considering the user information, and we believe this reflects the user's preference, and it combined with the user itself and in degree normalization, and to decide the temporal user representation. And that is the aggregator of the CF. And recently, people started thinking more complicated. So I don't mean this is the best one. And we often observe that it's just simple aggregator function without the weight, the multiplication of the weight in nonlinear layer. User preference based complicated aggregator does not work always, but it just give you some alternatives for your recommended system design. What about NIAGNN? So this is consider different type of neighborhoods. First one is from the drag neighbor, and this one is considering the interactions among neighbors. Because from the sampling, so we have this partial observation. Drag neighbor is from the green nodes, and each grid node is connected to the red nodes, and we are able to see we expect that they have some association. We believe that they are worthwhile to propagate information to decide the better node representation. So using different graph, we decide representation of the node and concatenation and decide neighborhood representation. So this is purely based on different graph construction from the samples and decide the final node representation. And this gives you the binary prediction procedure. So I haven't introduced about how to decide the final prediction score, or the user is likely to buy the product or not. We just considering now we have focused on how to decide user representation and item representation. So assume that we have some user and item representation, and when they are closely placed in the embedding space, we recommend the item. So for example, which is also very similar to the SVD based recommendation. Here we have the user. I'm sorry. This is user. This is item. So the location is from the final representation. So when it is similar, so we can compute the distance, right? And by using the distance, we can decide which item is likely to be used in their shopping mall or the Netflix, for example. So this is, let's say this is 1 and 2 and 3. So distance between the user and 1 is shorter than distance between the U and 2, the U and 3, right? So we think the item 1 is the best item to recommend. So we go into the procedure. So to do that, we need to get the final representation of the user and item. Now we are moving toward. So this is the example, not example. So the NIGN ends here this part computation. So if you have time and just follow the equations, it is simply decompose this into this and we get this. So it sounds very complicated, and complicated means computationally very expensive, but because it considers pairwise instructions, but their proposed computation is not fully pairwise computation, and so it is able to compute the this with the linear complexity. So you pay time and just follow the equation and understand what's going on there. So now we update representation, and now we have neighboring node representation. It's time to update considering the central node representation. So now you have neighboring node representation from the neighboring node and your own node representation. So you have two different types of representations, and we aggregate once again to decide the updated representation, which will be used at the upper layer. So the recent papers just aggregate, compute the the representation to decide to update the representation, and which showed the best result. And in their benchmark. But it could be, you can employ more complicated updating the computation, right? The concatenation and multiply by linear matrix and the bias and activation function, and you can decide. So it's up to you. But in the major benchmarks, and these worked better. So without this linear transformation and nonlinear activation function. That is the key observation from the recent papers. And compared to the linear combination, the concatenation operation with feature transformation allows more complex feature instruction, but it's the simpler one, the simpler work without the nonlinear activation, and the works contribute. I'm sorry. So the worked observed that the complicated the update function contributes a little to the overall performance, and they simplify the update operation. So went to the complicated one, now we're coming back to the simpler one. All right, so to decide final load representation, so due to the multiple neural network layer, we have multiple representation from the user U, from the first layer, second layer, this is from the HU, the Lth layer. It sounds natural to use the last one for the final representation. Think about your CNN and LSTM. So we use the final representation to predict the label. However, the representations obtained in the different layers emphasize the messages passed over different connections. So people observe that the last one not always showed good result, and people try to take advantage of the different representation, all the representation at the same time. So we may concatenate everything and connect to the fully connected layer and decide the final representation. This is one way. Second one is just mean pooling, and we just sum over every representation, or we can think about the weighted summation. But as we discussed before, the stacking too many layers, particularly from the GNNs, will lead to the over smoothing issue. So some works, these are proposed to adaptively balance the trade-off. So these are based on the ResNet scheme connections. So if you are interested, so I recommend reading those papers. All right, so now we are able to decide the final representation and item representation, and we are able to predict which item will be recommended. So we talked about integrating the other external information, and how we can incorporate the other networks, other information. So one of the popular ones is the social network. So in addition to the bipartite graph, we consider the GNN, the social network among the users, and we decide each user's representation at the same time, and the users representation came from these two, and decide the representation and predict the user is likely to be use the item or not. Another way is combine those two different types of the network into the one unified graph, and went through the GNN and decide the final prediction. So another way is to improve the existing recommendation is to use knowledge graph. So this is from the bipartite, and an item is often connected to the existing entities in knowledge graph. For example, we assume the item is from the song. We see that who is the singer, the genre of the song, the album title, and participated the artist, and these are presented in the external knowledge base, and we see their implicit relationships, and based on that we observed that these user 2 and 3 is related, and so these are discovered by the here knowledge base information. Right. What about sequential recommendations? Due to the time constraint, I haven't introduced all the details. So this figure shows the general idea of the recommendation. So we have talked about this notation, right? The sequential information is formed in the graph, and we learned the GNN. Now we have the node-wise representation, node-wise vector, and we can run sequence model. For example, we can learn the RNN, right, and find the sequence representation and predict something. So it depends your prediction task. All right. So if you are interested, I recommend reading and those survey papers. And any questions, let me know. Thank you for your attention, and see you soon. Bye bye.